Hi everyone, my name is Yoshifumi Nakata from the University of Tokyo. In this video, I'm going to explain our recent results about explicit constructions of exact unitary T designs and their applications to randomized benchmarking. So this video is based on our recent paper and it is already available on the archive. So if you are interested, please have a look. And here's an outline of this video. I would like to start with a brief introduction of unitary designs, and then I will explain our two results. One is about constructing exact unitary designs by quantum circuit, and the other is its application to benchmarking noisy quantum devices. So let's start with a brief introduction of unitary designs. So what is a unitary design? A unitary T design is defined as a finite set of unitaries that mimics a Haar random unitary up to the Tth order. So here we have another technical term, Haar random unitary, but this is a very simple object. So let's consider that we have n qubits and we are interested in the unitary operations acting on n qubits. So we have a unitary group of degree 2 to the n. And the Haar random unitary is just a uniform distribution over the whole unitary group. And here the unitary operators are distributed uniformly at random. And if we pick up one unitary from this uniform distribution, it is called a Haar random unitary. And unitary T designs are approximations of a Haar random unitary by a finite set of unitaries. So if we write a unitary T design in the same way, we have a unitary group and we have an ensemble of unitaries. Here in this figure, one yellow circle represents one unitary. So it's a finite ensemble. And we want to make this ensemble as uniform as possible. By doing that, we can mimic some properties of a Haar random unitary. And here we have one parameter t, and t is a positive integer. So we have one design, two designs, three designs, and so on. And if t becomes larger and larger, that means the distribution becomes more and more uniform. So we could understand this t as an indicator of how uniform, or I could say how random the distribution is. And in the limit of t goes to infinite, a unitary T design approaches a Haar random unitary. So this is a basic idea of unitary design. And the unitary designs have a long history in quantum information science, and there are two main questions. One is, how can we implement unitary T designs by quantum circuits? And the other is, what are the applications of designs? And much is known about unitary 2 or 3 designs. For example, we know that the Clifford group forms a unitary 2 and 3 designs for qubits. And this is good because Clifford group is relatively an easy group, so we can handle very well. And based on this fact, we have many quantum circuits that can implement unitary 2 and 3 designs, both approximately and exactly. And some of them are just Clifford circuits, so they are very efficient. We also have a huge number of applications of unitary 2 designs in quantum information processing. That ranges from communicational tasks, cryptography, computations, and some experiments. So in many fields of quantum information science, unitary 2 designs are very important. In contrast to the situation of unitary 2 and 3 designs, less has been explored for unitary T designs when T is greater than 3. And one difficulty in this case is that no group is a unitary T design for T greater than 3 in general. And so it is very non-trivial to construct a quantum circuit that can implement unitary T designs. And indeed, so far, we know only approximate implementations of unitary T designs for general T. And also, we don't know much applications. I also want to make one more comment about implementations of unitary T designs. So the study of unitary T designs started in combinatorial mathematics in 1970s. So like almost 40 years ago, they have started the idea of unitary designs. And since then, explicitly constructing exact unitary T designs for general T has been a long open problem in combinatorial mathematics. So it's highly non-trivial to construct exact unitary T designs explicitly. In this talk, we provide two main results. One is a quantum circuits for exact unitary T design for NUT, and the other is a new application of T designs for benchmarking noisy quantum devices. So let me explain a little bit more about each result. So first of all, we provide a quantum circuit for exact unitary T designs, and our construction is inductive in terms of the number of qubits. So that means we first construct an exact unitary T design on a single qubit, and we extend it to the larger number of qubits. So this is kind of good because this inductive steps shows me all the steps very explicitly. So all the gates in the circuit can be in principle written down explicitly. That means that we have solved an open problem in combinatorial mathematics. This is very good, we believe. However, due to this inductive construction, our quantum circuit has a big cons, which is that the construction is inefficient. So in this quantum circuit, we have to use exponentially many number of gates, unfortunately. So as a short summary of our first result, we believe that we made a solid progress of the theory of designs, but it is of practical use only in the constant size quantum system because of the inefficiency of the quantum circuit. And in the second application, in the second result, we provide a new application of designs for randomized benchmarking. So randomized benchmarking is a very common protocol for experimentally estimating quantum noises. And this is very standard method. So for example, in superconducting systems or like ion trap systems, we use these RB protocols very often. So it's a very common protocol. But we propose kind of generalization of randomized benchmarking based on an exact 2T, unitary 2T design. And we especially study the second order RB. Okay, so let me say that if we use an exact 2T design, we say the randomized benchmarking is an Tth order randomized benchmarking. And we especially study the second order RB. And we prove that we can estimate the self-adjointness of the noise in the system if we use this second-order RB protocols. And here, the self-adjointness is a new metric of the noise that we have proposed in this study. And we can argue that this self-adjointness is related to quantum error correction. So it's kind of nice if we get some information about the self-adjointness of the noise, because we can get some insight into the feasibility of quantum error correction. And based on our analytical studies, we already experimentally implemented the second order RB in a superconducting qubit. And we proved that it is actually feasible in experiment. So in the second result, we believe that we have contributed to the further developments of quantum information technology. So these are the short summaries of our main results. And in the rest of my talk, I would like to explain a little bit more details about our result. So let me first start with details of constructing exact unitary T designs by quantum circuits. So the basic idea of constructing exact designs is, as I said, we use inductive steps. So our construction consists of 3 steps. In the first step, we construct a unitary T design, exact unitary T design on U1. And of course, U1 is just a one complex number, so we can construct the T design by hand. And in the second step, we extend the T design on 1 qubit to that on U2. And of course, U2 is a unitary operation on 1 qubit. So by doing this second step, we obtain an exact unitary T design on a single qubit. And finally, we construct an inductive quantum circuit that can extend the exact unitary T design on n qubits to that on n plus 1 qubits. So by doing this, we can extend the unitary T design, exact unitary T design to any number of qubits. And the most non-trivial step in these 3 is the third step. So in the following, we focus on the third step. So to provide an inductive quantum circuit, we have to introduce 3 simple notations. So the first notation is Qn. So Qn is a unitary T design on n qubits. So here we have our new word, strong unitary T design, but this is not very important, so please forget about it. And based on this notation Qn, we define the controlled Qn. This is a set of n plus 1 qubit controlled unitaries. So here is a quantum circuit of controlled Qn. So depending on the first qubit, we apply a different unitary onto the rest of n qubits. So here is the definition of controlled Qn. And here U0 and U1 are chosen uniformly at random from a unitary T design on n qubits. And finally, we want to introduce Rx of theta. So this is a single qubit X rotation controlled by n qubits. So this is a quantum circuit. And we just apply a single qubit X rotation onto the first qubit. But the rotation angle depends on the n qubits. So this is the definition of Rx of theta. And in the next slide, we just write this Rx of theta in this way. So if you see some angle in the box, this is the rotation angle around x-axis. And obviously, this gate is not a 2-qubit gate, but it is easy to decompose this gate, n plus 1 qubit gate, into the series or sequence of 2-qubit gates. So if you see this one, please understand that this can be decomposed into 2-qubit gates. And our result is that if we repeat the controlled Qn and Rx of theta with an appropriate rotation angle, then we can generate an exact unitary T design on n plus 1 qubit. The statement is summarized in this theorem 1. So we showed that this quantum circuit is an exact unitary T design on n plus 1 qubits. As I said, this is just a repetition of controlled Qn and single Rx of theta with appropriate rotation angle. So we just repeat these two things. And to determine the rotation angle, we have to solve zonal spherical functions. So we have some function, and we just solve the function is equal to 0. And by doing so, we can decide the rotation angle. So what are the zonal spherical functions? I'm not going to give you a definition, but they are symmetric polynomials, and what is important to us is exact forms of zonal spherical functions are known. So they are polynomials, and we can explicitly write down zonal spherical functions. So in principle, we can compute the rotation angle. And by doing this procedure, and we just substitute these angles into these boxes, we can implement an exact unitary T design on n plus 1 qubit. So this is our main theorem in our first result. But unfortunately, this circuit is inefficient, and actually there are two sources of inefficiency in this circuit. So in the next slide, I will explain the two sources of inefficiency. So one source comes from the inductive steps. So here is a circuit of exact unitary T designs on n plus 1 qubits. But this is composed of several n qubit T designs. And to construct these T designs on n qubits, we have to use n minus 1 qubit T designs several times. So if we expand all the gates in this circuit, the number of 2-qubit gates easily explodes, and it becomes exponentially many. And that means this quantum circuit is inefficient. But I should also say that this construction is by far redundant. And we are pretty sure that there's a room for improvement. We are not sure if we can improve this scaling into polynomial scaling. Maybe it's very hard or impossible, but at least we can say that there's a room for improvement. But there's another source of inefficiency, which comes from the zonal spherical functions. We have to solve the zonal spherical functions, but the problem is that the number of variables in each function, they are just polynomial, but the number of variables in each polynomial is exponential in n. So of course, solving this is inefficient, at least classically. So maybe if we use some quantum technique or something, we could improve it, this, but we are not pretty sure about this. For these two reasons, our construction is useful only in small systems. But maybe the improvement is possible, so it's left open. Great. So these are the details of our first result. And next, I will explain the details of our second result about applications of unitary designs to benchmarking logic quantum devices. So our application is based on the generalization of randomized benchmarking. So in this slide, I would like to overview the randomized benchmarking protocol. The goal of the task is, for given noisy quantum gate set, we want to reveal the properties of the noise in the way free from state preparation and measurement errors. If there's no noise, well, of course, life is very peaceful, everything is very easy. But in reality or in experiments, everything is noisy. State preparation always has some errors, and gate action is always noisy, and also in the measurement process, we have lots of noises. And in this situation, the RB protocols try to estimate only the properties of noises on the gate. So we don't want to be bothered by state preparation and measurement errors. This is not an easy task because everything is noisy. But if we use a good technique of RB, we can estimate the noise only on the gate set. There are many RB protocols, but typically we use the Clifford group as a noisy gate set. So if we use the Clifford group, which is a Unitary 2 design, we can actually reveal the properties of the noise on the gate, such as the average gate fidelity of the noise and the unitarity, leakage error, crosstalk errors, etc., etc. So by using the Clifford group, actually we can get lots of insight or information of the noise on the gate. Our idea is, instead of Unitary 2 designs, we just want to use a Unitary 4 designs. And if this is the case, we just call the RB as a second order RB. And the protocol of the second RB is quite similar to the standard one. So I'm not explaining all the details, but this is the protocol of the second order RB in the rough sketch. So we prepare an initial state, which might be noisy. And we apply quantum gates, let's say M quantum gates onto the initial state. And we assume that these gate set and these quantum gates are chosen uniformly at random from a Unitary 4 design instead of Unitary 2 design. So this is a big difference from the standard RB. And one important thing is M. So M is the length of this gate sequence, but this is a very important parameter in the experiments. And after the application of this gate sequence, we apply an inverse operation. So if there's no noise, they cancel each other, so nothing happens. But if they are noisy, then they don't cancel exactly. So from this difference, we can get some information about the noise. So this is a basic idea of RB protocols. And finally, we perform some measurement of the observable, and we also do some post-processing. And post-processing part is also different from a standard RB, but I'm not going to explain the post-processing part. But anyway, the outcome of the second order RB protocol is a real-valued function V of M. Please note that M is the length of the gate sequence. So we perform this protocol for different M's, for different lengths. And then, as an outcome of this experiment, we obtain the function V of M. And we also assume that the noise on the gate set is identical. So it's gate independent and also time independent. This is a strong assumption, but this is somehow common in our RB context. So we just follow the literature and we assume this. And under this assumption, we can prove that from this real valued function B of M, the unitarity and self-adjointness of the noise can be easily estimated. So at this point, let me explain what is a unitarity and what is a self-adjointness of the noise. So first, unitarity is a metric of the noise which reveals how unitary the noise is. And this is known as a useful metric related to quantum error correction. This is because if the noise is coherent, if the noise is unitary, then it is hard to correct in general. So by checking this unitarity, we can get some insight into the feasibility of quantum error correction. So this has been already proposed several years ago, but in this study, we also propose a new metric of noise, which is a self-adjointness, and we argue that it is related to quantum error correction. So what is self-adjointness? Well, self-adjointness is a metric of how self-adjoint the noise is. And as I said, this is a new metric, and we can argue that this is also related to the feasibility of quantum error correction. And this is because we can easily observe that if the noise has a low self-adjointness, then it generally results in degradation of logical error rates if we use a standard recovery on operation, such as applying Pauli operations to the suitable set of qubits. So we want to have a noise. In the worst case, we want to have the noise with high self-adjointness. So this is kind of good because the error recovery is kind of easy in this case. So this is about the self-adjointness, and similarly to the unitarity of the noise, it's good to know how self-adjoint the noise is because it's related to the feasibility of quantum error correction. Anyway, these two quantities can be obtained from the experimental output of the second-order RB. And this is a theorem of the second-order RB on a single qubit. So this VM, so this is an outcome of the second-order RB experiment, can be decomposed into the sum of two exponential functions in terms of m. So in the first term, we have u to the m, and the second term, we have some value to the m as well. So this is just the sum of two exponential functions. And here, u is a unitarity of the noise, f is a fidelity of the noise, and h corresponds to the self-adjointness. So here we have the unitarity to the m, and the other one is just a linear combination of f, u, and h. So this is a numerical analysis. So let's say, this star point is each data point. And this orange curve is just a fitting of the experimental data. And obviously, we observe two exponential curves, right? And what is important is that the base of each exponential curve has an information of u, f, and h. So in this numerical case, the first exponentially decaying function corresponds to the first term. So from the decaying rate of this first curve, we can estimate the unitarity u. And we also have another exponentially decaying function, and from the decaying rate of this curve, we can estimate this linear combination of f, u, and h. And of course, we can also perform the standard RB, from which we can estimate f. So we know u, we know f, and we also know this one. So in the end of the day, we can estimate the self-adjointness from the experiment. So this is for the single qubit case, but the situation is quite similar for a multi-qubit case. But in the multi-qubit case, the experimental output of the second-order RB is a sum of 4 exponentially decaying functions. But the situation is nearly the same in the sense that the self-adjointness is obtained from u, c1, c2, c3, and the fidelity. So we just do the same procedure. We fit the experimental data by 4 exponentially decaying functions, and from that, we can estimate the self-adjointness of the noise. So in any case, by fitting the experimental data by 2 or 4 exponential functions, we can estimate the self-adjointness of the noise in the system. And based on these analytical results, we have implemented the second-order RB in superconducting system, and we obtained some result. And actually, there is a case where the fidelity is still high, more than 90%, but the self-adjointness can be less than 50%. So in that case, the optimal recovery is not so easy. Okay, so let me summarize my talk. So in this talk, we provided two results. One is about an inductive quantum circuit for exact unitary T designs. So this is the first explicit construction of exact unitary T design. So this is a very important step in the development of the theory of unitary designs. However, our quantum circuit is inefficient, so it should be improved. We also proposed a Tth order RB as an application of unitary 2T designs. And in this talk, I especially explained the second order RB using 4 designs. And I explained that we can estimate the self-adjointness of the noise in a very concise manner. And we also explained that the self-adjointness is a new metric which is related to quantum error correction. So future problems. There are lots of open problems in this study. For example, about construction of exact unitary T designs, as I said, our construction is inefficient. So it is very important to check if we can improve the efficiency of the circuit. So it is also interesting to point out that our proof technique is kind of new. So if we apply our new technique to the previous result of constructing unitary designs approximately, then maybe we can improve some part of the result. So this would be also an interesting direction to go. And also about Tth order RB protocols, I said that the self-adjointness of noise is related to the quantum error correction, but it is not quantitative. So it is very important to study quantitative relations between the self-adjointness of the noise and quantum error correction. So this is, I think, very important. And also, recently, there's a big development or big progress in the theory of RBs. So maybe it's possible to estimate self-adjointness by using lower designs. So in this protocol, we have used 4 designs, but maybe it's possible to estimate self-adjointness by 2 designs. If this is the case, it's very experimentally friendly. So this is also an interesting open question. So basically, that's it. So thank you for watching this video.